1 second. So, good morning. Okay. So I guess let's go ahead and get started. So does anyone have any questions that they want to look at? Any exciting things happening they want to bring up? Any Halloween costumes you guys plan on having on Friday? You're totally going to learn on Friday? Okay. Okay. So I just figured I was planning on dressing up as well, so if you guys would like to do so, feel free to. So let's go ahead and get started. So just a few quick announcements. So quiz 9 is going to be this Friday, covers lessons 23-24. So quiz 10. So in this case, it's going to be next Friday next Friday, November 6th to Saturday the 7th, covering lessons 25 and 26. So one thing I will mention before we get any farther is that there's not going to be any class next Wednesday due to that reading day we're supposed to have next week. So because of that, no class. So enjoy your free morning of class and or reading if you so desire, or just sleep in if you want, because it is 8:30 in the morning. And I won't blame you if you do that, because I will. So let's continue our adventure into optimization land and focus on some more examples. So this is the second of 3 lessons to discuss the idea of optimization, which involve setting up a function that we need to maximize/minimize. The process of optimization involves the following. So I'll just recall them from last time. So draw a picture, identify quantity to be optimized and what we can control/change, identify constraints, use constraints to set up an objective function for the quantity we want to optimize in terms of one variable. Differentiate the objective function, set it equal to 0 and solve. That's step 5. And then last step is just compute the desired quantity. Okay. So with that out of the way, let's go ahead and take a look at example 1 with this light in mind. Or at least part of it, because example 1 is going to be quite disgusting, as you'll see later. So the premise is that a Norman window is constructed by adjoining a semicircle to the top of a rectangular window, as shown in the figure below. So I'll just draw the picture, because then that way you guys will have it. So we have a semicircle to the top on the top of a rectangular window. Okay, that's our picture basically. So basically the premise is that if the perimeter of the Norman window is 22 feet, we need to find the dimensions that will allow the window to emit the most light. So basically what this says is that this perimeter is basically this part right here. So the perimeter of the window is this part right here. Just this part that's within the red part. So basically the perimeter, P, is equal to 22. So there's that part. And then what we're going to do is we're going to label the dimensions of this as, let's see. So here what we're going to have is, we're going to have X here. And here we're going to have Y here. So basically what this says is that, okay, we need to find the dimensions that will emit the most light. So in terms of our geometry, that means we need to, if we need to find the most light, that means we need to maximize something, right? So if we're trying to find the dimensions that will emit the most light, that means we should probably maximize what geometric quantity? Yeah, we got to maximize the area, right? Okay. So in this case, the area is focusing on the area of the rectangle as well as the semicircle. So what we're going to do is we're going to focus on the area of the rectangle for starters. So just a quick review, the area of a rectangle is, okay, good. So in this case, it would just be x times y, right? So we have x times y. So this is just the rectangle. Rectangle. Okay. So there's that part. And then basically, that's the rectangle. So now what about the semicircle? So if you recall, so if we focus on the area of a semicircle, what did you guys remember what that is?
Is it 1/2 pi r squared?
Yep, it's 1/2 times pi times whatever the radius is squared. Because remember, this part here, the pi r squared part, that's the area of a circle. So if you want the semicircle, well, just divide it by half. You're good to go. So this is the whole thing here is a semicircle if we divide by half. Okay. So if that's the case, that says, all right, so if x is the diameter here, what should that tell you about what the radius is in this case? Let's give someone else a chance. So if x corresponds to the whole radius of our semicircle, or the diameter of our semicircle, what should the radius be in terms of x?
1/2 x.
Yep, just x over 2, right? So just take our diameter, divide it by 2, and that's your radius. So essentially we end up with x times y plus pi x squared over 8. Okay? All right, so basically that says, all right, that's the quantity we need to optimize, and the things we can control / change are, in this case, the variables that we're given. So in this case, we control x and y to be greater than or equal to 0. Okay? So now, that's B. So now part C says, all right, so now we have to focus on our constraints. Okay. So the thing is that the problem says that we're given that the perimeter of the window is 22 feet. So that means, all right, so 22 corresponds to this whole perimeter here. So let's go ahead and break this down piece by piece. So if we focus on the rectangle part of the perimeter of our window, that must mean that in terms of the rectangle portion of our perimeter, that must mean we have what as our rectangular part of the perimeter? So I agree with 2y because of the fact that we have 2y here. But remember, this part is not included in the perimeter. So in this case, we only count 1x here. So we have x plus 2y for the rectangle. Okay. And then for the semicircle, what do we have? So in this case, we just focus on this part right here for the semicircle. So essentially, in this case, if you recall, the sort of way to express the perimeter of a semicircle is to, well, in this case of a circle, is to focus on its circumference, right? So do you guys remember what the circumference of a circle is?
2 pi r.
It's 2 pi r, right? So we have 2 pi r, so in this case, our radius is x over 2 as we just established. But then because it's a semicircle, if you want to focus on the perimeter of a semicircle, you have to take this and then do what? Divide by half, right? Okay. So then because of the fact that these two have the twos on top and bottom cancel each other out here, we have x plus 2y plus pi over 2 times x. So here's where things get a bit disgusting. So the thing is that after this, we basically say, all right, well, we can solve for either x or y, and then we plug this into our objective function to get this in terms of one variable. But the thing is, after a while, this does get quite a bit disgusting. So what I'm just going to say at this point is, there's a lot of details I'm gonna skip with this example because there's a lot of algebraic nonsense going on. Like here's all the algebra for this. So basically it's a lot. So I remember when I taught this class last fall, I spent like 25 minutes to 30 minutes on just this one example. I'm like, okay, rookie mistake, we're not doing that again. So what I'm gonna do is I'm just gonna say, if you really want to see the algebra on this, check the notes on my webpage. I'm just going to give you guys the answer from this point. Because once you guys have the area constraint, you guys can work from that and then go from there. So basically, at the end of the day, step F, we need to find the dimensions. So we just need to find x and y. So I'm just going to tell you guys, in this case you should end up with 44 over 4 plus pi, and y equals 22 over 4 plus pi. So one thing to keep in mind is that normally I don't just say here's the answer, work with it, but in this case I'm going to make an exception here because the algebra gets disgustingly long, and I'm fairly certain this does not seem like the kind of problem this will be on a quiz or exam. So you don't have to worry too much about studying this particular problem for the quiz or exam. But it's a good homework problem to look at, but it's not really a good exam problem or quiz problem. But I will conclude by saying a remark. Given perimeter P, desired dimensions are x equals 2p over 4 plus pi, and y equals p over 4 plus pi. So that way, whatever your dimension is in the homework, you basically just say, all right, well, set the perimeter p equal to whatever numerical value is here, plug it in, and then you're done. So, like I said, I usually don't like just saying, here's the answer, but in this case, in this one case, I'm going to make an exception. So, just something to keep in mind. Okay, so any questions on that? I know we skipped like a lot of everything, but just trust me, you don't want to spend like 30 minutes on this one example when we have more to focus on. So, okay. So any other questions on that? Okay. Does anyone still need to write this down? Okay. I'll take those now. Okay. So let's move on to some more sane examples. So let's look at example 2. So a box with a square base and no top is to be built with a volume of 8,788 cubic inches. We need to find the dimensions of the box that requires the least amount of material. And we need to also figure out how much material is required at the minimum. So let's go ahead and start with part A, because that's our picture. So in this case, we have a box with a square base and no top. So in this case, we can assume each face is rectangular. So in this case, you're going to have something that looks like this. So here's our box. Here's our okay. So one thing to note here is that we have a box with a square base. So in this case, that must mean our dimensions here are going to be what? So if we have a square base here and no top, that must mean, okay, if we sort of view this from this angle, box from the angle we're currently at, that must mean our box is going to look something like this. So you can see this part of the inside of the box, but you can't see this part of the inside. That's basically what's happening. So what we're going to do is we're going to say, all right, so if we have that this side of this length here is x, and this side of the length here is y, just to denote the dimensions. The fact that we have a box with a square base should indicate to you that the length of this side is also what? Just x, right? Okay, so in this case, that means we have x by y. Okay? Okay, so in this case, our goal is to figure out the dimensions of the box that requires the least amount of material. So the fact that we have least here should pretty quickly indicate to you we have to minimize something. So what exactly are we minimizing? So we have to minimize the least amount of material for the box itself. So what should that indicate to you regarding what we need to find here? What geometric quantity? So we're focusing on the material of the box. So in this case, we just need to focus on the individual faces, right? Surface area, right? Surface area. Okay. So in this case, what we're going to do is we're going to denote surface area, in this case, by S. Okay. So in this case, the fact that we have no top means we only have 5 faces we need to consider, right? We have the square base and then each of the 4 sides. So in this case, if you want to find the surface area, well, just focus on each individual face that's given to us, find this area, and then add them all up, right? So in this case, let's focus on the square base first. So the fact that we have a square here at the bottom means its area is going to end up being what?
X squared.
Yes, x squared, right? Okay. And then plus, well, let's see. What remains are the 4 individual sides. Now what you'll notice is that each of the individual sides has dimensions x by y, right? So the fact that we have 4 faces with dimensions x by y means that the total area of all 4 sides should end up being what?
4x.
Yeah, 4x times y, right? So we have basically the fact that we have 4 faces with area x times y means we have to just take the area of each face and then multiply by 4. That's basically what's happening with this. Okay? So that's part B. Now part C says, all right, well now what's our constraint from this? So the problem says that the box has to have a volume of 8,788. So that tells us, all right, well that means in terms of x and y, the variables given to us, that means 8,788 must equal what? X squared times y, right? Okay. So in this case, that should probably indicate to you, all right, in terms of the 2 variables that we have, which one do you think we should solve for in this case? Which will probably seem more optimal here. You gotta take a quick guess. Yeah, you want to solve for y here, right? Because if you solve for x, you're going to end up with square roots, and that's just going to get more disgusting. So, or at least it's going to be more work than is necessary here. So in this case, you want the constraint to get you y in terms of x. So y in this case is 8,788 over x squared. Okay? That's part C. So now part D says, all right, let's go ahead and plug our constraint into our surface area function to get the objective function here. So S equals, okay, so we have x squared plus 4 times x times y, which is 8,788 over x squared. So what this tells us is that, all right, well, we have x squared, that's the first term. Then if you multiply 4 by 8,788 to a calculator, well, you should be able to see that that's just 35,152. Okay, so that's these 2 constants here multiplied together. Then we have x divided by x squared, which simplifies to what quantity?
X on the bottom.
Yep, just x on the bottom, right? So that means our objective function is s of x, which equals this thing right here. So this is our objective function here. An objective function. Okay. There we go. Okay. So now, that's step D. So now we have our objective function. Let's go ahead and take our objective function, differentiate it, set it equal to 0, and solve. So we have s prime of x. So if we differentiate this thing with respect to x, then what should we end up with after applying the power rule?
2x minus 35,152 over x squared.
Yep, over x squared. So, okay, good. So now once we set this equal to 0, let's go ahead and solve for x from this. So, if we do that, well, one thing we can do is we can add this thing over to the other side. So we have 2x equals 35,152 over x squared. So in this case, what you should be able to pretty quickly see is that, all right, if we multiply x squared over to the other side, and then divide by 2, well, then you get x cubed is equal to, well, let's see, 35,152 over 2, which is just 17576. But one nice thing you notice about this is that, all right, that should pretty quickly tell you that x is just the cubed root of 17576. But here's the nice thing. If you plug this into a calculator, what happens?
Comes 26.
Exactly. It just becomes a very nice number, 26 here, right? So in this case, you end up with a fairly nice number here. Okay. So we have that, and then f. So that tells you the dimensions of the box that gives you the least amount of material. So that's one dimension. So then, in this case, the next dimension should be y. So if we let x equal 26 in our constraint here, that means we have 8,788 over x squared, which in this case is just 26. Okay. So then if you plug this into a calculator, you should end up with something relatively nice.
13.
Yeah, which is 13, right? Okay. And then from there, that will get you the dimensions that minimize the surface area. So dimensions that minimize surface area. So, okay. And then from there, if you want to figure out how much material is required at the minimum, then you can either say, all right, well, you can just plug in x equals 26 into your objective function here. And that will give you the minimum surface. That will give you the minimum surface area. Okay. So. Okay. So that's example 2. So any questions on that part? Okay. So let's move on to example 3 then, which will be even nicer. So that's if it's any consolation. So does anyone still need example 2? Okay. So example 3. So we now have our rectangular box again with a square base. So here's what's going to happen with this. So in this case, whether or not it has an open top or not is not really going to be too much of our concern here. So in this case, let's just go ahead and assume it does have a top face, even though we don't really need to worry about that too much here. So we still have our rectangular box with a square base, so our dimensions are still x by y. Now the sum of the height and the perimeter of the square base is 18 inches. So we need to find the maximum possible volume. Okay. So what you'll notice is that, okay, we need to find the maximum possible volume. So that should pretty quickly tell you we gotta maximize volume. Maximize volume. That's V equals, well, as we already established in the last example, that's just x squared times y. So nothing too crazy with that part. But now part C for our constraints. So here's where things get a bit more interesting. So the sum of the height and the perimeter of the square base is 18 inches. So with that being the case, we say, all right, so here's our, there we go, that's a bit better. Okay. So that means the sum of the height of the box and the perimeter of the square base equals 18 inches. So taking this into account, what should that tell you about what 18 can be expressed of in terms of x and y?
Y plus 4.
Right, because remember, y is the height, and then the perimeter of the square base, well, that's just 4x. So height, and then perimeter. Perimeter. Okay. So that gives you that part. Okay. So in a similar vein as to what we did in example 2, well, you should be able, in terms of what variables were given, it might seem more optimal to solve for which variable here. You got to take a crazy wild guess.
Y.
Yeah, it's better to solve for y here, right? Because in this case, even though it's not too bad to solve for x here, the fact that that means we're going to have to plug this into here, which means we have to expand something out, which ultimately makes things more of a hassle than they need to be. So if we just solve for y, we don't need to worry about expanding out. We can just distribute this x squared, and that's it. So in this case, we have 18 minus 4x is our constraint. So we have y in terms of x now. So now part D says, all right, so now the volume V can be expressed in terms of one variable as x squared times 18 minus 4x. So if we distribute the x squared, that should pretty quickly give you what the volume is in terms of x. So this will be your objective function here. So V of x. Okay, so this is our objective function. Objective function. Okay, so now what you'll notice is that, all right, well, so moving on to E, if we differentiate this and set it equal to 0 and solve, well, a quick application of power rules should be able to pretty quickly tell you this is just 36 minus 12x squared. Sorry, 36x, my bad. So if we set this equal to 0, then that should pretty quickly tell you, if we factor out the necessary things, that the two, in this case, the two values of x that solve this equation are what?
0 and 3.
Right, because if you factor out, in this case, 12x times 3 minus x. So if we set this equal to 0, that must mean that, okay, well, x equals 0 and 3, right? But wait a minute. If we let x equal 0, what happens to the volume? Yeah, it's just a big fat 0, right? So in this case, that's definitely not going to give us the maximum possible volume. So in this case, x equals 0 is going to be out of here. So in this case, we only care about x equals 3 here. Okay? Okay, so now we need to find the maximum possible volume. So now let's go ahead and take this dimension here, plug it into our objective function, and then we're done. So in this case, if we let x equal 3 inside our objective function, we have, well, 18 times 3 squared minus 4 times 3 squared cubed, sorry. So 18 times 3 squared minus 4 times 3 cubed. So if we plug this into a calculator or do the necessary mental math, then you should be able to get what as your final answer here. Go ahead.
So 54.
You just get 54 of this. Okay. And then because of the units given in the problem, that should tell you your units here should be what?
Inches cubed.
Yep, just cubic inches, right? Okay. Okay. And that's example 3. So, is there any questions on that? Okay, I'll give you guys a second to write that down. Okay. So moving on to example 4 then. So the premise is that the Pepsi company needs to make a cylindrical soda can that can hold precisely 1.7 liters of liquid. If the entire can is to be made out of the same material, we need to find the dimensions of the can that will minimize the cost. And we need to round our answer to the nearest 2 decimal places. Okay? So one thing to note here is that the volume of a cylinder is pi r squared h, and the surface area is 2 pi r h plus 2 pi r squared, with r the radius and h the height. And also 1 liter is 1,000 cubic centimeters. Okay? So part A, so let's start with part A. So we have a cylindrical soda can. So in this case, we're essentially going to have something that looks like this. So here's our cylindrical soda can. Let me make it look a little nicer, because that's not pretty. That's better. All right. Anyways, so in this case, the height of our cylindrical soda can is h, and then we're assuming our radius to be this guy right here. Okay. So here's the thing. So the problem says for the thing we need to optimize. In this case, it says we need to. Ultimately, the thing we're trying to minimize here is the costs. But here's the thing. We only need to find the dimensions of it, and there's not really any cost given to us in the problem. So here's one thing to note here. So cost of materials can depend on area of each part of can. So as in the top, the bottom, and the sides. But here's the thing. The entire can is to be made out of the same material. We don't know what it is. We don't know how much it costs. But the fact that we just need to find the dimensions, but same material, in this case, that just means it suffices to focus on the dimensions of the can that will minimize the surface area of our can here. It means we just minimize surface area here. Okay? Okay? So then our goal is minimize S equals, which the problem gives us as 2 pi r h plus 2 pi r squared. Okay? So like I said, even though the cost of materials can depend on the area of each part of the can, as we'll see next time, the same material and the fact that we only need the dimensions, we don't need the actual cost, means it suffices to focus just on the surface area here. But we'll get a bit more into the details of that next time. Okay. So now part C says, okay, our constraints. So we have to be a bit careful with this. So the thing is that in this case we are assuming that the radius and the height are to be in centimeters. So in centimeters. Okay. So here's the kicker with this. So even though the surface, so we're given that the can holds precisely 1.7 liters of liquid here. So in this case, that should pretty quickly tell you that the can itself can hold that much. So in this case, we can assume this will correspond to the volume somehow. So in this case, we're given that pi r squared h. In this case, that must mean that if r and h are in terms of, have units centimeters, that should tell you that this should equal what? So this should correspond to this somehow, but we need to get this in terms of cubic centimeters somehow. So using this part of the problem should tell you that 1.7 liters equals how many cubic centimeters?
1700.
Yep, 1700. Good. Okay. So then, as a result of that, and then using similar reasoning as the past two examples, in terms of solving for h, we get 1700 over pi r squared. Okay? So, that's our constraints. So if we plug this into our objective function, that must mean that s is equal to, let's see, 2 pi r times the height, which is 1700 over pi r squared, then plus 2 pi r squared. Okay? So what you'll notice is that, well, the pi's cancel out. This just becomes 1 over r. And then 2 times 1700, well, that's just 3400. So we got that over r, then plus 2 pi r squared. So that gives us the surface area strictly in terms of r. Okay. So the thing is that if we differentiate this and set it equal to 0, well, let's see what happens. So s prime of r will equal what? So if we use the power rule as we did in example 2, then we should be able to get what as our derivative?
Negative 300, 3400 over r squared plus 4r,
Yep.
4 pi r.
Plus 4 pi r. Good. So if we set this equal to 0 and solve, well, in this case, as for what we did in example 2, it seems like we're going to need to get this in terms of r cubed again first. So if we do that, so if we use similar algebra as to the second example, then that means that r cubed should equal what? And just focusing on exact values here, not decimal approximations yet.
3400 over 4 pi.
Yep, 3400 or 4 pi. Okay. So that should pretty quickly tell you, as after that, well, r should end up being the cube root of 3400 over 4 pi. So if you plug this into a calculator, you'll notice this is approximately 6.4677, just to give you an idea of what that's supposed to look like. Okay, so that gives you the radius. So now part F says, all right, now we just need to find out whatever else we need to figure out. So the good news is that we only care about the dimensions that minimize the surface area here. So in this case, once we have r, well, we can just go ahead and figure out, we can just plug that into our constraint 8 for h here to figure out what the height is. So in this case, we have, okay, well, 1700 over pi times, well, whatever r is. So in this case, cube root of 3400 over 4 pi. So in this case, if you use that, because that's what r is, and then square it, then you should be able to pretty quickly get that if you plug this into a calculator. This is just 12.94. Okay? Because in this case, we just need the dimensions here. Okay? All right. So any questions on that part? Okay. Okay. So does anyone else still need this? Okay. So now, last example. So the premise now is that a cylindrical Pringles can with its lid has a surface area of 113 square inches. And we need to find out the maximum volume with rounded to 4 decimal places. So the good news is, again, we still have a cylindrical can to consider here. So again, same picture as before, at least in terms of the last example. So in this case, this is still R. This is still H. So now, the problem states that we need to maximize the volume. So B says our goal is to maximize the volume. Okay. In this case, we have V, but in this case, the problem it gives us that explicitly as pi r squared h, so you don't need to worry too much about trying to deduce that here. So that's part B. Now part C says, all right, what's our constraint here? Okay, well, problem says that the surface area is restricted as 113 square inches. So that says, all right, well, that must mean that, okay, if we're restricted to 113 square inches, and here's our formula for surface area, well, that should pretty quickly tell you that 2 pi RH plus 2 pi r squared equals 113. Okay? So in this case, what we're going to do here, just to make our lives a lot easier, because the other way is much worse, we're just going to go ahead and solve for h here. So if we do that, why don't you guys take a second to solve for h in this case? So if we solve for h with regards to this constraint given to us, what did you guys get for your constraints?
I'm sure if this is right, but 113 over 2 pi r minus r.
Yeah, that is right, but I think what I'm going to do is I'm just going to write this in terms of a slightly different one. So what you'll notice is that, so let's take a step backward. So the thing is that if we want to solve for h, well, let's subtract this 2 pi r squared over to the other side. So we have 2 pi r h equals 113 minus 2 pi r squared. So if we divide then 2 pi r over to the other side, then we should end up with h equals 113 minus 2 pi r squared over 2 pi r h. Oh, wait, no, sorry, just 2 pi, sorry. Okay, so then that will give us our constraint. So let's erase that a bit more. There we go. So that gives us our constraint. So now h is now completely in terms of r here. So now, if we plug this into our objective function, we have v equals pi r squared times, well, let's see, h is this, so we have 113 minus 2 pi r squared over 2 pi r. So what you'll notice is that a lot of things cancel out relatively nicely here, don't they? So in this case, the pi's here, they cancel out because top and bottom. And then what you'll notice is that we have r squared over r as well. So that means this squared here cancels out with this r downstairs here. So ultimately what we're left with is r times, well, 113 minus 2 pi r squared over 2. So then what does that tell us? So in this case, well, for the inside we have, if we distribute this 1/2 to both terms on top, then that means that we can express this as what? So we have 113 over 2, but then we subtract that with the second term, this 2 pi r squared over 2, but, well, that just simplifies to pi r squared, doesn't it? So ultimately what we're left with here is 113 over 2 times r minus pi r cubed, so that's your volume in terms of r here. Okay. So, is everyone okay with how I got that? Any questions on how I got that part? Okay. All right. So now, moving on to part E then. Now let's go ahead and differentiate this and set it equal to 0 and solve. So, if we differentiate this as we've been doing, well, power rule should tell you this is just 113 over 2 minus 3 pi r squared. So if we set this equal to 0 and solve for r in this case, that should tell you that r is equal to what exact value? Where are you getting a negative from?
Negative 3 pi.
But if you add this over to their side, you should get it positive, right?
Add other.
So then, yeah, you have r squared is then 113 over 6 pi, right? But then, so then, as a result, if you take the square root of both sides, and note that r has to be positive because it's a radius, that means it's 113 over the square root of 113 over 6 pi corresponds to the exact value for the radius here. So then if you plug this into a calculator, then you'll notice this should be approximately 2.4484. So that's our first dimension rounded to 4 decimal places. Or at least that'll just help you give you the maximum volume. So, because now F is we got to find the maximum volume. So in this case, we have, all right, so if we plug in V of the square root of 113 over 6 pi, and then we plug this into our calculator and solve, we have 113 over 2 times square root of 113 over 6 pi minus pi times square root of 113 over 6 pi cubed. Okay, so if you plug that into a calculator and round to 4 decimal places, what should you get as your final answer here?
92.2244.
Yep. So if you plug that into a calculator, you get 92.2244. And because of our units given in the problem, that should be, our volume should be in terms of what inches? Cubic inches. Okay. Okay, and that's example 5. So, any questions on any of that? Okay. Alright, so that's all I have for today. Like I said, I'll see you guys either on Friday or Zoom office hours. And like I said, if y'all want to dress up on Friday, I will not be opposed to that, since I will do that as well. So, alright. Otherwise, I will see you guys then.